So we'll start the state variables today. So the state variables or the state space analysis is a new dimension for analysis of the system. Okay, so whenever we have a system being represented by maybe a differential equation representation or any other time domain equation representation or the frequency domain equation, irrespective of that, we define what is called as a state. All right, so first let's look at the concept of state, how the state is defined, and then we'll move on further, uh, seeing how the concept of state can be used for analysis purpose. Okay, so let's consider one example, right? We have a voltage source, and let's say we have a resistance and maybe a capacitor, and this generates a specific voltage. Let's call that as an output voltage. All right, so this is a supply voltage denoted as V in. There is a resistance R, there is a capacitance C, and we are measuring the voltage. This is V out, right? So we know that if you want to find out the output voltage, right? So that is V out. If you want to find out V out, what are the conditions or what are the various parameters you should know? So I repeated my question. If at all I want to find out the voltage, which is the output voltage, right? If I want to find V out, I know V in. Okay, so yes, I know the V in, I know R, I know the value C. So there's no unknown here. Okay, so my question is that under such condition, if you want to find V out, what are the various parameters you are expected to know? Yeah, what are the, okay, maybe current. Fine, current is one thing. Any other? Or I'll ask the same question in a different way, which may give you some idea, right? If you know V in, right? Again, you can apply KVL, KCL, anything to find out the current. Let's assume, okay. In order to find V out, is it necessary that you need to find out anything else other than V in, right? Because V in is known. Any other voltage is required, or only V in is sufficient? That's maybe that will help you out a little. Um, okay, so V in is being applied at t equal to 0, let's assume. Okay, but you know that the capacitor actually stores some voltage, isn't it? So you see, if at all there is some voltage that is existing across the capacitor before you apply V in, right? If at all, right? If at all you have a initial voltage across the capacitor, then that's going to change the way of calculation here, right? V out changes if you have a initial voltage. V out is pretty much straightforward to calculate if you don't have any voltage across the capacitor, right? So uh, only the information about V in is not sufficient in that case, right? Because if at all you have an initial capacitor voltage, that must be known. Right, now you see, right, let's try to go to the exact point now. So if at all you have a system, right, where the output is not just dependent on the input but also on the initial condition, right? Here this is such example. So output depends upon the input as well as the initial condition. right? If at all you have such a situation, right now we can see that. So initial condition in the sense, any past value, right, is it's going to affect any past value that is right, that was present earlier in the circuit, is responsible for the current value of your output, which means, right, the system has memory, it has to remember what was the previous value, correct? So such systems, it's called as the memory. Okay, it indicates that I can write the system with the memory. So what's the other name to this? If you remember, this is also called as a dynamic. So dynamic system. Already we considered that in the previous sessions we tried to solve the problems using Laplace transforms and initial conditions, right? So whenever you had a differential equation, you apply the uh, initial conditions to solve, correct? So that itself is a dynamic system, right? Now uh, I'll ask a slightly modified question now. What if I replace the capacitor C by another resistance, say R2? What happens to the system now? Is it dynamic or it's something else? Shall I repeat the question? So in this circuit, if I replace the capacitance C by another resistor, right? Maybe a different resistor, say R2. Now, will this new circuit is dynamic or it's changed? It's something else. Only two resistors, no capacitor in the circuit. It's not dynamic, right? Right. So there is no question of storage of energy. So when you don't have the storage of energy, you don't get a dynamic equation. So basically, the dynamic equation is something when you relate different parameters, you get a differentiation or integration coming into picture. Right. So the current in a capacitor is C dV by dt, correct? So you see that current requires the rate of change of voltage. At the same time, if you want to calculate the voltage, it's 1 by C into integral I dt. So integral I dt is nothing but all the currents that, right, passed through that capacitor from minus infinity to that till that time, correct? So because of that, it's a dynamic system. Right. So now I'll write the other point as well because differentiation is important. So if the output is dependent only on the input, right? This implies, right, no memory. So the no memory system or a zero memory system, this is also called as zero memory. Okay. So a zero memory system is referred to as a static system. Anyway, so as of now, the static, we already considered static throughout, right? So now we are moving to the dynamic systems, and we already have seen how to solve the equations at a first stage, right? So if you have a dynamic system represented by a differential equation, how to proceed, right? That part we already have seen. Okay, now the next objective here is to understand the state. So to understand the state, let's go for another representation. So let's consider a mechanical system first. This makes it very easy to understand, so I'll use a mechanical system. All right, so let me say I have a mass over here. This is a mass and I'm applying the several sets of forces onto this, right? And this is going to generate the outputs in terms of, okay, the output of the system uh, maybe, okay, in terms of two variables, let's assume. So on one side I have the force, this is capital F. So there is a system denoted by its mass m, and let me assume that we have two variables, right? One is v and one is x. So v represents velocity and x represents the displacement. Okay. All right. Under such a condition, now we know something about the mass, how the force and the masses are related uh, in general. Okay, I'll show you this. Okay, so we know something, right? We know that I'll directly write F is equal to m into, this is mass, into acceleration, right? So m is the mass, a is the acceleration. We know about this, correct? So this is also equal to the mass. Okay, I think I wrote capital M. Let me follow the same notation throughout. Okay. Okay, so let's say that this is m into a. So this m acceleration can be written as derivative of velocity v of t by dt. Okay, so this implies, what if I want to calculate v of t? This implies the v of t, if I want to calculate, how do you write? Correct. So I have to do the reverse process, correct? So this implies the v of t should be equal to, can I write 1 by m, 1 by m times can I write integration, I make f as a function of time, so let's write it as f of t dt. Okay, is it fine? Okay, now so let's proceed one step further. Now if it, now you see this integral is basically from minus infinity all the past values, correct, until the current time, right? So this is what is the meaning of the force. So what we do now, we'll try to split this. So this is equal to 1 by m, I'll keep 1 by m as it is, right? This is integral, say minus infinity until the time you give the force f, right? So assuming that the whenever you apply the force, right, onto that object of mass m, that is considered as a time t equal to say 0. Okay, until then, so before that whatever was the force that was existing over there, we call this, that's the minus infinity to 0 f of t dt. This is the first part, plus 1 by m integral, this is maybe 0 to t, in the sense once you apply that force, what happens, f of t dt. So this is the second part, right? So the time equal to 0 indicates the initial time. So here t equal to 0 is the initial time, where the time begins, time counts. All right. Now you see we can try to write this as, it can actually be changed. Some of the textbooks will also say that you can call, you don't have to write 0 over there, right? T naught is the initial time. You can write that as well, because sometimes you see there may be a delay in applying the uh, force, right? Force is applied at t equal to 2 seconds, possible. So if that is the case, right, I'd like to write it in general, right? So t equal to 0 is initial time. So if we say that the t naught, right, uh, let's denote it by some other value t naught. Okay, so if I say that t naught is the initial time, then we can write the v of t like this. V of t is equal to 1 by m integral minus infinity till t naught f force f of t dt plus this is 1 by m integral t naught to current value, that is t, f of t dt. Okay, so that particular value, whatever we are writing now, is the time t naught till t is the value we need to calculate. But now you see this value, this is going to be fixed, right? It cannot change now. Yeah. So this is going to change dependent on the t value, whatever is the t that you are going to consider, right? This term will change, correct? The second term will change. T changes means your integral will change, because of which you can see that the value will ultimately change, right? But the right, that's the initial term. Minus infinity to t naught is going to be, t naught is fixed, so minus infinity to t naught, that particular value is a constant, right? I know that this is a velocity component at t naught. You can write v of 0 as well if you consider t naught as 0, right? So this is called as the initial velocity. Initial velocity plus this, the second term, gives you the total value of the velocity. Again, this is just an example. The same concept can be applied even for the circuit example which we took earlier, right? You can actually calculate the volt V out, that depends upon the initial value of the voltage across the capacitor plus. Now we understood something. Initial conditions or the memory, right? This is the memory value, right? So this initial velocity itself is the memory. So you see, dependent on whatever the memory of the system's characterization and the subsequent behaviors will change, right, of a system, right? So that's what is very important to understand. Now this leads us to the concept of state. All right, so therefore I can write one thing, the memory, or we can call the initial conditions. I can write affect, initial conditions affect the system characteristics. Maybe it also includes the output, the behavior, what input generates what kind of output, etc., will be altered by this. So now we come to the concept. I will try to define the state, right? Therefore the state is actually uh, it's a compact representation of the past history of the system, right? So we simply wrote it. So though you are considering the values from minus infinity till some value t naught, right, the whole thing you represent as a v of t naught, correct? It's a compact representation. So state can be considered as a compact representation of uh, the past, or it can be the history of a system. So basically the state of the system briefs about uh, what happened in the past, and it actually separates the future, right? What exactly is going to happen after you apply some force, right? That is being separated, right? From the total value, you separate the initial value plus the future value, right? So the past value becomes equal to a state of that particular system, right? So now let's go to a specific representation of state at a given time t, right? So now I understand from the, again I'm talking about the same equation which we have written so far, right? So that is uh, something like, at a given point time t, right? We understood that you combine the values of all the different elements of the system that are associated with the initial conditions of the system, right? In this case, in that case, maybe it is just a velocity, right? But if you have two capacitors, maybe both the capacitors, right, are going to put their efforts in the initial conditions. Maybe voltages across both of the capacitors you might have to consider to calculate the final value. Correct? So now I try to slightly modify this equation, this statement which I have written. So I just have written in general. This sentence was in general, right? So complete state. When can you say a complete state? I want to define a complete state of a system. So this is what is the actual state. So previous one was just in general, okay, just a general statement. So it is right. We can try to write the initial conditions of every element, right? I have maybe two inductors, three capacitors. So inductors are also going to have memory, right? Current in an inductor looks like a memory element, right? So you can see that inductor will have some currents, right? Initial currents I1, I2, I3. uh, Across the capacitors you have some initial voltages like V1, V2, right? So totally five elements are in your circuit, means you will get a vector, right? You try to write in a matrix, correct? So these are the initial conditions of my circuit, right? Like that you will write. We have seen it, seen them in the network analysis, right? So a vector having components which are the variables of the system, they are closely associated with some initial conditions, right? So that whole vector will be called as a state vector representing the complete state of the system. So basically I'll try to write that statement now. Complete state indicates it's a vector. It's a vector having the components, having some components which are the variables of the system with initial conditions. With the initial conditions, right? So, right, generally, in general, what is the notation given? It is capital X of t, right? So this particular vector is called as a state vector. Okay. When I say state vector, it's normally a n dimensional vector because there may be n different elements. All right. So, for example, let me write a general notation. This is an example. The x of t may contain x1 of t, maybe voltage across first capacitor, x2 of t, voltage across second capacitor, x3, current across an inductor, right? x4, x5, and so on. Like that, you may have xn of t. Like this, we write. So you can see that the each one of them, x1, x2, x3, right? They are the state variables of the system, right? I'll write any xi of t. This is a state variable. It's a variable because that value is a variable, right? Whatever you store there, initial values are different, correct? Okay. So that's how we try to define now. So if let's consider say the state at t is equal to t1, right? I want a specific time t1 where I want to decide what is the state of the system, right? So you must know x of t naught, where t naught is the initial condition, correct? So that's what is the meaning now. So overall what we understood so far is that. So the new state will be x of t1 that depends upon the past values, right? Plus, so whenever the value of the t is greater than t1, right? So for example, at in order to calculate the value at t equal to 2, you should know what is t equal to 1, correct? Similarly, if I extend the concept to t equal to 3, you see t equal to 2 becomes your initial condition. Maybe, like that. All the past values until some time, t naught can be anything. As of now, what we understood was initially I mentioned that it is 0. But later on we updated to t naught. Any t naught can be considered as a general initial condition. Right. So at t equal to t1, if you are considering all the values before t1 is the initial condition, can be used as initial condition, and any value t greater than t1, the t equal to t1 becomes the initial condition, right? Okay, now so how many state variables you are going to consider, right? So we'll write, this is again in general, the general way of representation. So for a given system, the number of state variables. What should be the number of state variables of a system, right? This is always determined by the order of system. Number of state variables equal to order of a system. Okay, this is the first thing to remember. If the order of the system is 4, I should have 4, right, state variables. Again, there is one more point here. Out of the state variables you choose, right, some of them are called as independent, right? So the values are independent of other state variables, correct? So this is the next point to remember. The number of independent state variables of a system, right? Okay, this is always equal to the number of energy storing elements in that system. Okay, equal to the number of energy storing elements in the system. Okay, like capacitors in terms of voltage across a capacitor, or the inductor in terms of the current through that inductor, etc. Right, it depends on, it depends in that way. Okay, now let's go ahead and look at the same concept of state variables being applied to a second order system. Okay, so this is an example, right? Consider a second order system, right? So as the order equal to 2, this implies what is your conclusion? Number of state variables required equal to 2, right? Number of state variables equals to 2. So right, let's try to denote that x of t in terms of, it's a vector, it should contain two elements. Now one is x1 and one more is x2, correct? Why so? Because it should have two, correct, two state variables. It has to be represented by using a vector. So the vector we defined is in this fashion. Right, whenever it's a vector we understand something. So the concept is like, if you want, it's a vector, so if you want to write using the vector notation, the x of t, make it a vector. That is nothing but it is the vector x1 of t plus the vector x2 of t, correct? Because that's a vector notation. right? So if at all you say a vector, say vector A is 2 3, right, in a coordinate system. Let's try to write a coordinate system quickly, right? So if at all I want to write a coordinate system like this, so this is the first variable, this is the second variable, x2. So you have to move 2 units along the first one, right, and the 3 units along the second one to reach this vector, right? So you see this is the vector, this point represents the vector, right? So the vector A is this. So you see here, and trying to represent in this fashion. This is vector A. So there are 2 units here, 3 units here. So that's what is this 2 is corresponding to first. This is for the second, x2. So like that, it means you are adding. So 2 units along x-axis, in a sense horizontal axis, 3 units along vertical axis to reach A, vector A. So that's what is the representation now. If I write x1, x2 here, it actually means this. Right? So now at time, say at time t1, right, at time t1 I can also write this as, so at t equal to t1, it should still hold the same representation, in the sense if I write x of t1 should be equal to x1 of t1 plus x2 of t1, isn't it? X of t1 should be equal to x1 of t1 plus x2 of t1. So physical meaning is that you are going to add up the two components of a vector to get the complete representation of that vector. So that's what is indicated here. So we will add up those components like x1 of t1 plus x2 of t1 to calculate the state of that system, or x, that the capital X at a given time t1. Yeah. Okay, this should hold good even for, right, the t2. In general, you can generalize this as at t equal to t2. Also, this is true. Yeah. Right. So you see, we have. Okay, I'll come to a different notation now. Let me write two equations for the time being. Okay, so at say t is equal to t2, let me write another equation. So that is x of t2 is equal to x1 of t2 plus x2 of t2. All right, this is fine. We understood, right? So anyway, this is just an example. So let's write. So x of t1 I try to write as a, okay, I'll go for a bigger graph now. All right, just to make it more clear. So we need these equations, x of t1 and x of t2, right? How to calculate that we understood now. But now we define what is called as a trajectory, right? How the states are changing with respect to time, we try to understand that. Okay, so let's say, so we have the similar coordinate system at t1 and t2, let's assume, and let us say initially the x of t1 I try to denote using, say, one vector. That vector be like this. Okay, This is the first vector in denoting the x of t1. It's x1 of t1 plus x2 of t1, right? X1 of t1 you obtain over here, x2 of t1 you obtain from the y-axis. Okay, so this is the horizontal axis basically represents x1 and the vertical axis is x2. All right, so x of t1 is this. Now let me change the color and let me denote the x of t2 at a different time t2. The state of the system is represented like this. Let's see. Okay, it changed because dependent on the past values, it's going to change, right? So let's assume that this is the x2 and x1 and x2 like this. So this denotes the x of t2. So obtain like this equation. Okay, fine. Now you see the, if at all, let's assume that the t2 is greater than t1. In the sense t2 comes later, t1 comes first. So from t1 your state of the system changed to its state at t2 is x of t2. You can see that the state has been changed from x of t1 to x of t2, isn't it? So just see, right? So the red colored line indicates that the state is changing in this order, in this direction. Okay, right? So this actually is what is called as the state trajectory. These are the words we need later stage. So this is called as the trajectory or general state trajectory. So x of t1 can be considered as the initial state, x of t2 is the final state under this condition because they are calculated at t1 and t2. Yeah. Okay, all right. So we try to define few of the terms now. Okay, now let's go for the state model. This is also equally important. It's the next topic is called as the state model. So we make some assumptions now. Let us consider what is called as a nth order multiple input, multiple output system. Okay, we are going to consider a multiple input, multiple output system now, and it is of the order n. Okay, in the sense the equation of that system is of nth order. Okay, yeah. So let's try to write a model for that. So this is the, so if you remember the short form for multiple input multiple output is MIMO, correct? Yes. Multiple input multiple output. So let us try to denote, see the number of inputs are not expected to be equal to the number of outputs. That's the first thing, right? So I will assume different numbers now. So let's assume that there are a certain number of inputs to this system. So there can be any number of inputs. So we call this as say u1, u2, dot 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 up to um. So these are the inputs of the system, and since this is multiple input multiple output, we write it as a MIMO system. Okay, and the number of outputs can be completely different. All right, so because of that, let's write some other a different number for the outputs. So let's call this is y1, y2, and let's say we have p number of outputs, it's different. Okay, so they are the outputs of the system. Now since we defined that it's a nth order system, now what are the number of state variables you are expecting? It's n, right? Because we already defined that if you have n as the order of the system, right, then there should be, right, n state variables. Okay, so we use that to define the state variables. Again, we know that the state variables are going to change. That's why it represents a variable now. So just to denote that they are the variables of the system, we try to give again some outputs representing them. So let's say this is x1, x2, dot 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 up to xn, right? So these are the state variables of that particular system. So here, let me write what we assumed so far. So the number of inputs equal to m. All right. So the number of outputs are assumed to be p. So if at all the inputs u1, u2, u3, dot 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 up to un can be represented, their instantaneous values can be represented in the form of a vector. Okay, then okay, just let me go back. Okay, if at all you are able to represent like that, then what should be the u of t matrix? If at all I want to bring the matrix format, saying that every value you write inside this matrix are the instantaneous values. Like u1 has a value u1 of t at a given point of time t. It may be a variable, like u of t, u1 of t may be a sine value, sine function, sinusoid. But the point here is that, right, whenever we have that kind of representation, the u1 of t represents the value of that function at time t. Okay, like that you see that you have m such possibilities. So u2 of t dot 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 up to u m of t, isn't it? This is a matrix. So what is the size of this matrix? It is m rows, one column, so, correct? And what should be the matrix representation of your output? So this also y1 of t, y2 of t, and we have p number of variables. So this is yp of t, each variable indicating the instantaneous value of that variable at a given time t, correct? Okay, so this means what is the size you are going to write now? This is p cross 1, isn't it? And we already have defined the state variable whichever we are trying to write, right, is right of size n, right? Its order is n. So therefore x of t is nothing but this is x1 of t, x2 of t dot 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 up to xn of t. This is standard. N is the order, so I am going to use n number of state variables to write the matrix. Okay. The state space, or we already have defined this, right? Now, so I know that each one of them, right, each one of this, what you call state variables, are dependent on, right, two things. One is the initial condition and your input, so that the next value can be predicted. What happens to x1, right, in a next time, right, that you consider a small change in time, t becomes t plus delta t, correct? So right now it is time t. Let us assume that t becomes t plus delta t, correct? In under such condition, what happens to the x1 of t? X1 of t will definitely change, correct? So that small change in a value, small change in the value of a variable, when you change the time, is nothing but the differentiation, correct? What do you mean by dy by dt? When t changes by a small amount, what happens to y, correct? What is the change in y? So same thing you are going to apply now. So similar concept we are going to apply now to understand the concept how we bring the differential equations into place, because we already know that this is a dynamic system. We are considering it a dynamic system means it has a memory. So how the past values are going to affect your next values is what we are trying to understand here, right? So I'll write the state variable representation can be uh, arranged in uh, n different first order differential equations, right, as follows. So that means what I mean, see, x1 can change, you can calculate it dx1 by dt, correct? X2 can change, you will write another equation dx2 by dt. Like that I have n different equations, so definitely you can write n different equations, right? So those n different equations will create, right, what is called as n different first order equations. Are you okay with that? Correct. So that's what I mentioned just now over here. So n different equations we have written. So this indicates, I'll write the equations now. So therefore this is d x1 of t by dt is actually, so the standard representation is x1, above that you write a dot indicating that this is a state variable representation. X1 dot means it is derivative, okay? Now on what all parameters this depends upon, it depends upon, I'll write it as a f1, it's a function of all the initial conditions x1, x2, x3 dot 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 up to xn. All the past values will decide what happens to the change, comma all the inputs, correct? u1 comma u2 dot 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 up to um. Are you fine with this? Do you need any explanation for this? Why you are writing x1 and u, x1 x2 up to sn, xn, and u1 u2? Correct. So current value of the voltage across a particular capacitor, right, is my x1. Okay, assume, right? So that voltage may dependent upon all the other capacitors and inductors. That's why x2, x3, x2, xn comes into picture. Also, you may have three different inputs. From one side you get a voltage, other side you are taking a current to the circuit, right? So all those values will also, right, change the state of your variable. Voltage across that particular capacitor might change dependent upon what is u1, what is u2 up to m number of inputs you are taking from different sides to the circuit. Everything will change. That's why all the state variables plus all the inputs will change your state of a particular uh, state variable, correct? So dx by dt, right, the change of your state variable depends upon all of them. But what extent, to what extent each variable, each of the state variable x1 to xn and u1 to um changes a particular variable is different, right? Right. So for that, you see, now I change something like this. So dx2 by dx2 of t by dt, which is nothing but it's a x2 dot of t, is a different function. It's not f1, it is f2, because, right, the way in which all the state variables and all the inputs affect your second variable is completely different compared to the first variable. That's why, so the variables are still same. It's x1, x2 dot 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 up to xm comma u1 dot 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 up to um. So that's all. Okay, so like that, let's go to the final equation. Yes, definitely. Okay, so all the past values will define, right, your current output plus the current inputs also is going to affect that, right? Like that you can consider. So in general, I'll write the last equation dxn of t by dt should be equal to, this is xn dot of t, that is nothing but a function fn which decides how these state variables like x1 comma x2 dot 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 up to xm comma the inputs u1 u2 dot 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 up to m are going to affect, right? We still can make these functions f1 f2 fn as another vector, right? So I can write, if I write f is equal to say f1 f2 dot 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 up to n, right? Okay, dot 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 dot, it's fn. This basically denotes a functional operator. We can try to write in that way. Okay, now if you write a differential equation like that, definitely I can try to write, I can convert this into the integral format, correct? So this implies I can I write xi of t as, see, this is xi of t naught, correct? Because some initial condition, current value is nothing but initial value plus integration from t naught till the current value of your function, whichever function is going to decide that, you can use that, right? Fi of inputs x1 x2 all the values up to xn comma the u1 u2, right, up to um, and since you are doing the integration with respect to time, I have to write, sorry, I have to write a dt at the end. Okay, so this is into dt into dt, right? All right, so using that we can try to represent the system, right? The current value of the system can be defined in this way. So what could be the I values? Now we are generalizing that, that's why I can take 1 2 up to n value, because there are n different states, isn't it? Now, okay, it's a n dimensional time invariant system, right? How do you represent the state equations in that case, right? So there are n different states possible. So again, this is a general equation, so therefore in general I can write the x dot of t as a function of all the x and all the u. Okay, so this is one part. Again, let's look at the same thing in a different way, right? I can actually calculate the output of the system, right? So you see the y of t also, I'll write, this is also, it's again, this is a general equation. So if I want to write y of t, this can be calculated as another function, another g of its x comma u, correct? See, the output of the system depends upon the current inputs and all the past values, that is x, correct? So, but a function will be different now. So you have to use a different function g, correct? So again, g is also a different functional operator. Right. Now we give specific names now. So the names are as follows. This first equation, whatever you are able to write for a given system, is what is called as the state equation of a system. Okay. The state equation simply represents that. Also, the y of t equation which we write, right? This is called as the output equation of a given system. All right, now we'll try to write a general representation of this system. The general representation goes in this way. It's again a simple block diagram. Okay, we'll try to write a generalized block diagram, and that could be like this. And say this is the input, and from here, let's assume we are taking it out, and say this is u of t input, this is the y of t output. So u of t actually takes in another value, that is x of t naught, correct, which is the initial condition, right? This u of t can be taken and provided mixed with the output to get the instantaneous input, right? Plus this is x of t, right? That comes after u of t and x of t all together will be, sorry, u of t and x of t naught all together, you get x of t, which is clubbed together to get your y of t. That's it. So this is the dynamic representation of a system, right, considering the initial states as the state variable. So x of t naught is your initial state, the x of t represents the combination of all the state variables in that in the form of a state vector. So overall, this is the idea we need to understand the whole concept of what is called as the state variables.